Hello and welcome to chapter 7. So if you recall in chapter 6, we introduced the normal distribution. And the normal distribution follows this curve here, where the majority of our data falls in the middle. And then we have small amounts of data that fall outside to the left and small amounts of data that fall outside to the right. And that is all if you were to take an individual and look at that individual's outcome. But what we're going to do in chapter 7 is we're going to take samples, and we want to see how the samples vary from each other, from sample to sample. So I'm going to do this example activity with you. So it says X is the length of time in days that a cookie recipe lasted at the Olmsted homestead. So recipe 1 lasted 1 day. They ate all the cookies in 1 day. Recipe 2 lasted 5 days. So you can see that they did 60 recipes all the way over here to the bottom right. And you can see, for instance, recipe 48 lasted 11 days. So they may not have liked that one as much. Okay. So if you click on the Desmos link, for the chapter 7 intro, you're going to see all of the data, all 60 pieces of data. And then I found that down here, I found the population mean and standard deviation. So on average, a batch of cookies lasted 3.57 days with a standard deviation of 2.148 days. Okay, so these are my in units. This is how long the batch lasted. Okay. So I went ahead and I took 4 samples of 5 pieces of data each, and I found the mean of each of the samples. So my sample 1 had 5 data pieces and it had a mean of 2.4. The second one was 4.2, the third was 3.8, and the fourth was 4. And then I found this was the mean of these values. And then this is the standard deviation of these values. Okay. Then I said, well, what if we were to take samples of size 10? And so they're all in, you can see my samples in size 10 in Desmos link. And here are the averages of those samples. And again, those averages are very close to the average of our population data from here. But when I take the standard deviation, they don't look like they're varying from each other very much. This 4 sample had a fairly large mean, but the other 3 were very much similar to each other. So we can describe the 2 different sets. So the groups of size 5, they had the average of 3.6, and they were very close as far as their standard deviation was only 0.816. And the samples of size 10 were very close in the mean from the population, but their standard deviation was even smaller at 0.3697. So you can see that our population distribution was something like this. This was all 60 of the recipes. And then when we took samples of size 5, we had about the same center, but it became a little bit tighter because that we had that smaller standard deviation. And then when we took samples of size 10, it became very tight here. And so that's what we're going to look at today. Is we are going to, for the rest of the semester, we're pretty much going to be looking at how does a sample compare to the population. So in the previous sections, we looked at how does an individual compare to the population, but now we're going to look at how does a sample compare to a population. So let's jump into the examples for chapter 7. So it says, suppose that X is a random variable with a distribution that may be known or unknown. So we have to remember that. Using the subscript that matches the random variable, suppose, so I'm taking the mean of my sample means, okay? So the mean of all sample means. And then this is the standard deviation of all the samples. Then as n increases, the random variable x bar, so my sample mean, which consists of sample means, tends to be normally distributed with this. So my sample, the mean of all the means, is going to get very close to just my population mean, but my standard deviation has to be offset. So I'm going to take this, the standard deviation of the x bars, really, that should be divided by the square root of n. Okay, so by dividing by the square root of n means that as our sample size gets bigger, the samples are not going to vary from each other very much at all. They're going to all be very close to each other. So we have to offset by dividing by the square root of n. So it says the central limit theorem for sample means that if you keep drawing larger and larger samples, such as rolling the 1, 2, 5, and finally 10 dice, and calculating their means, the sample means form their own normal distribution, the sampling distribution. Okay, so this is establishing what we're going to call the central limit theorem for sample means. Okay, so we're going to be, you'll notice in your sample, in your formula packet, that this is something that we have to establish every time we do confidence intervals, which will be chapter 8, and hypothesis testing, which will be chapter 9, and so on and so forth. We have to verify these 3 conditions. So suppose there is a population of size n with mean mu and standard deviation sigma. A sample size of n is selected such as the following conditions are met. So the first condition has to prove that we have a random sample. Each observation is collected randomly from the population. Condition 2, independence. So observations are independent of each other. If the sample is collected without replacement, then the population must be at least 20 times larger than the sample size. So either 20 times the sample size has to be less than the population, or, so you can do either of these calculations, or the sample size has to be less than 5% of the population. And then the third condition that we have to meet is normality. So if we tell you that the population distribution is normal, then we're okay. Or our sample size has to be bigger than 30. Or I'm going to give you a probability plot to show you that. So there's 3 possibilities that you can use to verify conditions number 3. Okay, so when we talk about describing the distribution, we are going to talk about the shape. We're going to assume it's approximately normal. Once we have met these 3 conditions, we're going to say that the center, the average x bar, is going to be approximately the mean of the population, and that the spread of the x bars is going to be the standard deviation divided by the square root of n. So I'm going to show you how we're going to work these on paper along with those notes so you can follow along. Lots of examples today. An unknown distribution has a mean of 45 and a standard deviation of 8. Samples of size 30 are drawn randomly from the population. Find the probability that the sample mean is between 42 and 50. Okay, so even though our distribution is unknown, we have sample sizes of 30 so that we can go ahead and say that our conditions have been met, because we know that we took random samples. They told us that. And we are going to assume that we've met the independence. And then for normality, we have samples that are greater than or equal to 30. So we're okay there. So the mean that we're going to use is going to be 45. And then the standard deviation we're going to use, standard deviation of the means, is going to be using this here, the sigma divided by the square root of n. So we have to use that in Desmos. So we're going to use 8 divided by the square root of 30. And we want to find the probability that x is between 42 and 50. and the mean is at 45. So let's mark where 42 is somewhere over here, and 42 is only 3 below 45, but 50 is 5 above. So they're just it's a little bit further over here. Sorry, 50. Okay, so we want to know the probability of this. So let's go to Desmos and check it out here. So this is example 1. And so our mean, I'm going to enter that, is 45. And our standard deviation is 8 divided by, and I'm going to use my menu down here to do the square root of 30, my sample size. And then I want to be between 42 and 50. So it looks like 97.9, so 0.9797. So approximately 98% of my data is between 42 and 50. Okay, let's go to example 2. Okay. Example 2 says, the length of time taken on the SAT for a group of students is normally distributed with a mean of 2.5 hours and a standard deviation of 0.25 hours. A sample size of n equals 60 is drawn randomly from the population. Find the probability that the sample mean is between 2 and 3 hours. Okay. Now, unless I ask you to specifically prove the 3 conditions, assume that the conditions have been met. Okay. So let's write out what this means. We want the probability that the sample mean is between 2 and 3 hours. So our distribution is X bar is going to be normally distributed with a mean of 2.5 and a standard deviation of 0.25 divided by the square root of n, which is 60. So this is what we're going to be using in Desmos. And let's just draw our picture here. The mean is at 2.5, and we want to know between 2 and 3. Here we are. Go to Desmos and put that in. So you got your picture drawn, and we're going to go and put in our parameters into Desmos. And I'm going to copy this and put that there, and our mean is 2.5. And we have 60, and there we go. So we want to find the cumulative here between 2 and 3. So very, very likely. Let's see, this is what our picture looks like. There's our average at 2.5. So it's almost 100% likelihood. It gives us a 1, but that's only because it's using not very many decimals. So approximately 100% of the data. Go back and show you my paper here. And actually, because the standard deviation is so small, 2 and really were out here, right, when we saw the picture in Desmos. Desmos is very accurate compared to our drawings. Okay, let's look at examples. Example 3 says, in an article on Flurry blog, a gaming marketing gap for men and for men between the ages of 30 and 40 is identified. You are researching a startup game targeted at the 35-year-old demographic. Your idea is to develop a strategy game that can be played by men from their late 20s through their late 30s. Based on the article's data, industry research shows that the average strategy player is 28 years old with a standard deviation of 4.8 years. You take a sample of 100 randomly selected gamers. If your target market is 29 to 35-year-olds, should you continue with your development strategy? So let's just see here. We want to, our idea is we are trying to get late 20s to 30s, but our average, it's normally distributed 28 and then standard deviation of 4.8 divided by the square root of 100. And it says if your target market is 29 to 35-year-olds, we want to know what percent is actually between there using the data that we know about the market. So the average is 28, and we are looking at between 29 and 35, we'll say here. So we want to know what is the likelihood of being in there. Because it shows that the average player is 28 years old with a standard deviation of 4.8. So let's just see if we're targeting the right group here in our research. So the mean is 28 years old. And we've got a sample of 100. So let's just see how they're distributed here. And we're looking at the likelihood between 29 years old and 35. So the probability is not very big, 1.86% likelihood. I'm not sure we chose a good situation. So that's between 29 and 35. Show this on our paper. And I should be writing X bar here on all of these. These should really be X bars because we're not taking the individual, we're taking samples. I apologize about that. So the likelihood of our sample being between 29 and 35, because that's my target, is pretty small because actually the average age is 28. So our target market, we really should be targeting younger, it looks like. So the market is younger for sure. It says cans of a cola beverage claim to contain 16 ounces. The amounts in a sample are measured and the statistics are given here. We get a sample of 34 with a mean of 16.01. If the cans are filled so that the mean of 16 ounces is labeled with a standard deviation of 0.143 ounces, Find the probability that a sample of 34 cans will have an average amount greater than 16.01 ounces. Do the results suggest that cans are filled with an amount greater than 16 ounces? I'm guessing that they're actually filling them with less these days. So let's just look at the probability. So the probability that the mean, so greater than is what they're wondering. So greater than 16 ounces is the question. So it says find the probability that a sample will have an average amount. So we're testing bigger than this. Bigger than 16.01. We want to know what that is. Well, the mean is at 16. 16.01. We want to know what is the probability of being over here. This is our question. Oh, and let's just see here. The mean is normally distributed with 16 as the average and 0.143 divided by the square root of n, which is 34 cans. So let's go put that into, that's 34. Let's put that into decimals. $16. And 34 was in. This is what our picture is, but we want to know greater than, so we're doing greater than 16.01. And that's our, you can see our shaded space here in the green. This is what we drew in our page. And it looks like that likelihood is 0.3417. So approximately 34.2%, it looks like, of the colas are actually have more than 16.01 ounces. So very interesting. Example 5. Example 5 says, in the United States, someone is sexually assaulted every 10 minutes on average, according to a number of studies. Suppose the standard deviation is 0.5 minutes and the sample size is 100. So let's just draw. This should say A, B, and C, not A, B, and D. Okay, so we don't need this picture here, but let's just write, we are, the sample is normally distributed with mean of 2 and standard deviation of 0.5 divided by the sample size of 100. Find the median, the first quartile and the third quartile for the sample mean time of sexual assaults. So the median is where 50%. Okay, so these are interesting because now we're given percentages and we want to find the outcome. We want to know the number of minutes. We know the average is 2. We want to know the median where 50% is below. So what we learned in chapter 6 was that inverse CDF. So if we go back to Desmos, that inverse CDF right here. And we have to put in our mean of 2 minutes And the 0.5 divided by square root of 100. And then we want to look at 50%. So we already know that just from our data, we should have 50% that fall below there, right? So that one should be, the median should be 2. It should. But the first quartile, Q1, is the probability of what X, what sample mean that's going to be less than, first quartile is 25%. So we want to know where 25% is. And the cool thing is, let's just mark this one here. This is example 5. So let's go back to our paper for just a minute so you can see what I'm writing down. So our median is 2. That would be 50% is above and 50% is below. So we want to know where 25% is. So let's just mark 25. And so we're trying to find that value. And that just came up as, because remember, if we know the area, we can put that in with the inverse CDF. In Desmos, let's go back and see what Desmos told us that was. Right here, inverse CDF with the normal distribution. And we said that was 1.966. 25% of the assaults happen less than 2 minutes, every 2 minutes. Let's look at the third quartile. That would be 75%. So Q3 would be 0.75. How often are 75% of the data? So let's just make that one here 0.75. And it looks like that's every just over 2 minutes, 2.03 minutes. Letter B says, find the probability that a sexual assault occurs on the average between 1.75 and 1.8 minutes. So here's the average, and we said 1.75 to 1.85. And so what is the probability that it occurs between that number of minutes? So let's go back to put in our normal, because this time you want to find the probability. And cumulative, so we need to put that in, and we said 1.75 It's not very likely. 0.0013. So not likely at all. And then part C, part C says find the value that is 2 standard deviations above the mean. Okay, so if the mean is at 2, and if we want to find the 2 standard deviations above the mean, we're looking for an X value that is right here. And 2 standard deviations right here. But we are talking about not just standard deviations, but we're using, our new standard error here that is offset with the standard, with the sample size. So we don't need this. We need 0.5 divided by the square root of 100 is 0.5 divided by 10. So we're going to look at that in decimals here. So let's just put 0.5 divided by 10. So that's 0.05. So 2 standard deviations would be the mean, which is plus 2 times 0.05. So 2 plus 2 times 0.05 is 2.1. So that is the end of example 5 in the first part of 7.1. It's pretty lengthy, so I thought I would break up chapter 7.1 into a couple different videos. So catch me back for starting with example 6.